Hello class, today we're looking at chapter 5, the number theory and real number system. Today we'll be looking at chapter 5.4, the irrational numbers. So we looked at the rational numbers in chapter 5.3, now we're going to look at the irrational numbers. Because if there's rational ones, there has to be irrational ones. Kind of like people. Alright, our objectives here. Number 1, we're going to define the irrational numbers. Number 2, we're going to simplify square roots. Number 3, we're going to perform operations with square roots. And number 4, we're going to rationalize the denominator. So that even if it's irrational, at least the denominator is rational. Let's define irrational numbers. The set of irrational numbers is the set of numbers whose decimal representations are neither terminating nor repeating. For example, a well-known irrational number is pi, because there is no last digit in its decimal representation, and it is not a repeating decimal. So pi is approximately 3.1415926535897932238846264338327995, etc. There's no terminating or repeating aspect of it. Let's look at square roots. The principal square root of a non-negative number n, written as the square root of n, and this notation here is the square root notation, is the positive number that when multiplied by itself gives n. For example, the square root of 36 is 6 because 6 times 6 is 36. Notice that the square root of 36 is a rational number because 6 is a terminating decimal. However, not all square roots are irrational. Now, I say a lot, there are square roots that are irrational and there are square roots that are rational. So let's look at it. A perfect square is a number that is the square of a whole number. For example, here are a few perfect squares. 0 is a perfect square because 0 squared is 0. 1 is a perfect square because 1 squared is 1. 4 is a perfect square because 2 squared is 4. 9 is a perfect square because 3 squared is 9. The square root of a perfect square is a whole number. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Let's look at the product rule for square roots. If a and b represent non-negative numbers, then the square root of a times b is the same thing as the square root of a times the square root of b. And the square root of a times the square root of b is the same thing as the square root of a times b. The square root of a product is the product of square roots. So essentially we can split the square root up if we need to, or we can combine the square root as needed, as long as it is the same root. Simplify if possible. A says the square root of 75, B says the square root of 500, and C says the square root of 17. The simplification of square roots is something we really do need to know how to do. Now, in order to simplify this square root, as you see with A, the whole idea is that you try to break it up into factors of the original number, and at least one of those factors be a perfect square. So here we can break 75 up into 25 times 3, which is what we do. We say the square root of 75 equals the square root of 25 times 3. We then break that square root up into the square root of 25 times the square root of 3. We know that the square root of 25 is a perfect square, so the square root of 25 is 5, which reduces this down to just 5 times the square root of 3. This is the idea behind the entire system. To break the first number up into two numbers that are factors of the first number, at least one of which being a perfect square. Let's look at B. Now, if we look at 500 and try to think of what factors of 500 could break up into a perfect square, we come to the conclusion that those factors should probably be 100 and 5. So 100 is a perfect square, 5 is not. But 100 times 5 is 500. So we break the square root of 500 up into the square root of 100 times 5. And then we break that square root apart into the square root of 100 times the square root of 5. The square root of 100 is 10. And that leaves us with 10 square root 5. Now, we look at 17 here with C, the square root of 17. 17, the only factors of 17 are 1 and 17, neither of which are a perfect square that's going to help us. Now, 1 is a perfect square, but if we pull out a square root of 1, we're still left with a square root of 17, and we wind up with 1 times the square root of 17. It really doesn't get us anywhere. It doesn't buy us anything. So because 17 has no perfect square factors other than 1, it cannot be simplified. Alright, let's look at multiplying square roots. If a and b are non-negative, then we can just use the product rule. The square root of a times the square root of b equals the square root of a times b. Kind of like what we just looked at, but kind of working a little bit backwards to multiply these square roots. The product of the square roots is the square root of the product. Ooh, I think I went too quick. So, jumping all over the place here, sorry. So, let's multiply these examples here. Example 2, multiplying square roots. The square root of 2 times the square root of 5 is simply the square root. We can combine those square roots. The square root of 2 times 5. Now, the square root of 2 times 5 simplifies to the square root of 10. If we could simplify this further, we would. But 10 has no perfect square root, and it has nothing that we can break it down into that is a perfect square root, so we just simply leave it alone. If we look at b, the square root of 7 times the square root of 7, that simplifies to the square root of 49. We know the square root of 49 is a perfect square. That's just 7. So we have done 7 times 7 is 49. The square root of 49 is 7. It is possible to multiply irrational numbers to obtain a rational number for the product. If I look at C, the square root of 6 times the square root of 12, and I combine those, I'm looking at the square root of 6 times 12. 6 times 12 is 72. So I'm looking at overall the square root of 72. Now, if I think about the factors of 72, 36 is a factor of 72, and it has a perfect square, or is a perfect square, because the square root of 36 is 6. So we're going to break this 72 that we multiplied to get back down to a 36 times 2. The square root of 36 is 6, so we simply reduce down to 6 square root 2. If a and b represent non-negative real numbers, then b is not equal to 0. Then the square root of a over the square root of b equals the square root of a over b. And the square root of a over b equals the square root of a over the square root of b. The quotient of two square roots is the square root of the quotient. So it kind of goes both ways, just like multiplication. Let's find the quotient. I'm looking at the square root of 75 over the square root of 3. That is the same thing as the square root of 75 over 3. We know that 75 divided by 3 is 25. And the square root of 25 is a perfect square. So the square root of 25 is just 5. The next example says let's try to find the square root of 90 over the square root of 2. Okay, well I'll combine that and say that's the square root of 90 over 2. 90 divided by 2 is 45. 45 isn't a perfect square though. 45 needs to be broken up. 9 times 5 give me 45, and 9 is a perfect square. So that works. So I'll break this up even further into the square root of 9 times the square root of 5, knowing that the square root of 9 is 3. So this simplifies to 3 square root 5. We can also add and subtract square roots. So it says the number that multiplies a square root is called the square root's coefficient. Square roots with the same radicand can be added or subtracted by adding their coefficients. So we get a times the square root of c plus b times the square root of c equals parentheses a plus b square root c. So the sum of the coefficients times the common square root. We can also do this with subtraction. So a square root c minus b square root c equals a minus b times the square root of c. The difference coefficients times the common square root. So let's add or subtract as indicated. Here we have the 7 square root 2 plus 5 square root 2. This should mean that we should be able to do 7 plus 5 in parentheses times the square root of 2. 7 plus 5 is 12, so that should give us 12 square root 2. This has the common root of root 5, and it's a subtraction here, so I should be able to do 2 minus 6 times the square root of 5. 2 minus 6 is negative 4, so this should reduce down to negative 4 square root 5. If we follow the solution, we see that we are indeed correct. 7 square root 2 plus 5 square root 2 equals 7 plus 5 square root 2, which reduces to 12 square root 2. And if I look at 2 square root 5 minus 6 square root 5, this reduces to 2 minus 6 square root 5, which reduces to negative 4 times the square root of 5. We rationalize the denominator, so we're going to look at rationalizing the denominator, to rewrite the expression so that the denominator no longer contains any radicals. We don't really want radicals in our denominator. That's the whole purpose of what we call rationalizing the denominator. So the process of rationalizing the denominator is, if you do have a radical in the denominator, you want to get rid of it. So if you have a square root in the denominator, we want to get rid of that. Here we have 15 over the square root of 6, and we want to rationalize this denominator. Essentially what we're doing is saying, I don't want the square root of 6 in the denominator. I don't like the square root in the denominator, so we're going to rationalize it. Okay? In order to do that, we're basically going to multiply by this one term here that is made up of the radicand that's in the denominator. So we're going to take 15 over the square root of 6. We're going to multiply it by the radicand that's in the denominator, square root of 6 over square root of 6. What then happens is the numerator is simply 15 times the square root of 6. But the square root of 6 times the square root of 6 is just 6. And that radical goes away. You could do the math to work up to that, because square root of 6 times the square root of 6 equals the square root of 6 times 6 equals the square root of 36. And we know the square root of 36 is 6. And that's how we get this 6 here. If we can reduce, we do. So here 15 over 6 reduces to 5 over 2 because 3 goes into both of those terms. So I take 3 out of both of those terms and reduce this to 5 square root 6 over 2. Now, it wants me to rationalize the denominator in the second one. And the original one they give me is the square root of 3 over 5. Now the reason they want me to rationalize this is technically we have a radical in the denominator because it breaks down to the square root of 3 over the square root of 5. I want to get rid of this square root of 5 in the denominator, so I had to multiply by the radicand that's in the denominator, the square root of 5 over the square root of 5. Okay, 3 times the square root of 5 gives me the square root of 15, because 3 times 5 is 15. The square root of 5 times the square root of 5 gives me the square root of 25. And we know that the square root of 25 is 5. So this reduces us down, to the square root of 15 over 5. Now the square root of 15, there's nothing I can pull out factor-wise that will reduce here. So the square root of 15 over 5 is our most reduced form here, and would be our answer after rationalizing the denominator. This completes chapter 5.4. If you have any questions, please don't hesitate to reach out to me by email. I hope you have a good rest of your afternoon. Please attempt your homework. And like I said, any questions whatsoever, don't hesitate to reach out to me by email. Y'all have a good rest of your day.